Okay, so welcome back to today's class. So in today's class, before we introduce what we have for you today, I want to kind of refresh your mind on what we studied in the previous class. So in the previous class, we took a classical example of and tried to design the tree, right? So there you were able to compute the entropy of the entire data set and even the individual entropies. Followed by calculating, you were able also to compute the average information entropy. And then finally, you found the information gain. And then you see there was an issue, I don't know if you noticed that, where we had two nodes that actually gave us the same entropy. Okay, sorry, the same information gain. So in such a case, we somehow went with one, right? And we chose one, and then we were able to arrive at what? Our pure leaf nodes. Now in today's class, we will look into the hypothesis search space in what? Decision tree learning. So first, we will start by looking at the hypothesis search space with insights into the search strategy. How is it different from the hypothesis search space of candidate elimination? And look at the capabilities and the limitations, or say constraints. Followed by inductive biases in decision tree. So here we are, remember we studied inductive bias in what? Candidate elimination, remember? Yes. So the same thing, we are going to look at it now, okay? Inductive bias, how is it actually different from the inductive bias of candidate elimination, right? Here we will look into what we call preference and what? Restriction biases. And then why do we prefer shorter what? Hypothesis? That will lead us to studying Occam. Actually, he's actually William of Occam. Okay, so we get into that. I don't know why it's called Occam razor, but yeah, fine. Now, we move into looking at the arguments that are in favor of the shorter hypothesis and the one that opposes it. Right? So let's get started. ID3 can be characterized as what? Searching a very huge hypothesis space, looking for that one that fits what? The training example. That single hypothesis that fits the training example. So this the hypothesis space searched by ID3 is the set of what? All possible what? Decision trees. You saw that, right? Even we designed a decision tree to maybe help you accept a job offer or not. And then also that one that will enable you to play tennis or something. And you see, it's kind of an inexhaustible possibilities, right? Because all the possible decision trees, okay, if we increase the data set, can be enormous, right? And it might even lead us to situations where we will not be able to what? Arrive at what? A logical conclusion, right? So again, we say ID3 performs a simple to complex hill climbing strategy through this hypothesis space. Now, again, you say, okay, you've studied hill climbing, right? Okay. Don't worry, if you've not studied, you get back to your previous notes and then you look into that. So here, what do we mean by this studying this mirroring the hypothesis space of hill climbing? Because it starts with an empty tree. Then it does what? It considers progressively more elaborate hypotheses in the search decision space, right? Looking for one which classifies the training data. So if we see, when we saw something like this, okay, you know definitely how we arrive at the outlook being our root node. So we saw something like this. And then with that, we considered all what? The possible attributes, right? So there and there. So we know that this was overcast or something. Now here again, we decided, see, this has to be split and that also should be split, no? But the question was, which one should I prefer in this, right? So again, I went with one, okay? You can also start with the right node, no problem. So this is what, we are still at the first level of the tree. Now again, with this, you split, right? Just imagine if this has 3 more splitting conditions, okay? So 1 or 2 and 3. So you'll be left with the question, which one should I choose now? Should I split this first or that, right? So here, this was my root node, no? Initially it was empty, we started from here, okay? And then we moved, or we go that way, again continuing, right? Until we're able to get what? Arrive at our what? Pure leaves. Say here we got a pure leaf, right? So this we dwelt more on it in the previous class, okay? Now, if you view this in terms of each search space and search strategy, there are some insights which we can draw from what? ID3. So first point, we say that ID3, the search space of ID3 is a complete space of finite discrete valued function. So finite discrete valued functions that represents what? Sets of all possible attributes. So the second one, lack of current hypothesis. Current hypothesis. It keeps track of current hypothesis as it searches through this what? Space of the decision tree. So the third one is that what? ID3 in its pure form does not perform backtracking in its search. So here you say here, no backtracking. Okay, backtracking in English is very simple, right? It's self-explanatory. It's a process of you going back and checking what actions you performed that led to a particular solution, right? So if it didn't lead to a solution, again you check. Example, you want to write a program that will find the sum of 2 numbers, very simple program. When you wrote the program, maybe, okay, let's look at prime number for now, okay? An example. So in the prime number program, you know that definitely 1 cannot be a prime number. The first prime number is 2. So what happens, if you check in the sets of numbers 1 to 10, you see the prime numbers and odd numbers, they look alike. See, odd number starts from 1, 3, 5, 7, 9. Then prime number 2, 3, 5, and 7. So 9 and 1 are missing. So what happens most times, students will tend writing programs to find whether a number is odd or even. Now you know definitely that, okay, 1 is not a prime number. Then you have to go back and modify your program. So that process is known as backtracking. It's giving some output, but it's not maybe exactly what you expected, right? So you go back. In ID3, it doesn't support what? Backtracking. So we say ID3 in its pure form does not support backtracking in its search, right? So that means once it selects a node to test for a particular level in that tree, it never goes back and reconsiders its choice, right? You saw that in the example of the tree we just drew in the previous class. See, whenever we choose, say, attribute equals rainy or whatever, windy, we didn't bother, okay, will this converge? Okay, can we just go back? So we just went like that. So, right, I told you it's more like a waterfall model. So it never backtracks. So we remember again that ID3 uses all training examples at each step in the search space to make statistical based decisions regarding how to form the current hypothesis. So let's make it brief. That uses all training example in each step. So the fourth point uses all training examples, EGs. Right. So with this, you can actually try to see what might be the limitations now. Let's look at this. See, we explained the search space and limitations together. So I want you to figure out what are the limitations of the ID3 search strategy. What are the limitations? The limitations here, no backtracking. Is it a limitation? Yes, so it's a demerit. Limitation. Now, so it's capable of taking all the training examples. Yes, so this is an advantage. Okay, classify the other one now. Finite discrete valued functions, and it keeps track of all the current hypotheses. Fine. So keeping track of all the current hypotheses, is that an advantage or a disadvantage? You find out. It's an advantage, right? So keeps track of that. So this is also an advantage. Okay. And then you look at this. So it utilizes finite discrete valued function. That also is an advantage. Now, the next thing I want you to do is to find out two more limitations of what? The search strategy of ID3. Is that fine? Okay. So with that, we move to the next point, which is inductive bias in decision tree. So if I throw a coin first time, there are only two possibilities, either head or tail. Now, when I told you that, think of this, I am Virat Kohli, okay? So yes, so I want always to go first. I want to bat first. Oh no, I have to decide, right? So I'll say head. If head appears, then I should decide, right? So now I just take my chewing gum and attach it to that side, okay, to the head section. So when you flip the coin, obviously one side is heavier, right? So it will land on the other side. I'm like, yay, I got head, fine, take it. So that coin is biased, right? So initially, I have a pure outcome, right? Either yes or no. I introduce an external force in form of what? Putting some substance there. Even you've heard of ball tampering and stuff, right? So which bowlers do? Fine. So here, when we talk of what? The inductive bias in decision tree, is it that, there will be some external force in which we are going to add as in the game? No. So here there are assumptions, right? So there are assumptions. So inductive bias of decision tree is the set of assumptions that together with the training data deductively justifies the classification assigned to the learner for future instances. See, what I know for sure in my candidate elimination, right? We have this assumption that we need to get a version space, right? Is that right? Fine. So we have to get a version space. Only then we know that, fine, we are done with that, right? So we consider sets of what? Specific hypotheses, and again general hypotheses, and the intermediary was our what? Our version space, right? So these are assumptions that we must definitely give in sets of specific hypotheses. Initially we start with empty hypothesis, right? Null. And then generic hypothesis we must get as what? The version space. The same thing here. But here there are typically many decision trees that are consistent with those examples. I'm just giving a reference to our candidate elimination because again we use the same data set for our ID3, right? So you see, in that same case, okay, where we got the hypothesis, the version space, there are many decision trees that are consistent with that example. That leads to the question, which of these decision trees should ID3 choose? Which one should it choose? Because here you cannot say, okay, this is Packer what I should choose, right? This is the first one I should choose. So that is the inductive biasness in this ID3, okay? So what is the inductive bias in ID3? It is confused now on which decision tree it has to choose. That is consistent with the training example. Fine. So here it has to implement a strategy, right? So the strategy it will follow is first it will select what? Shorter trees over longer trees. See, it's basically, maybe when you write the program, the iterative program, then you will understand. So let's put this here. Usually ID3 is biased, okay? Where it has sets of possible trees that conforms to the what? Unique example. It will do what now? It will choose shorter trees over longer trees. So the question was, which of these decision trees should ID3 choose? Which decision, I will use DT for short, okay? Which decision tree to choose from the list of, of many that are consistent, with the what? Training example. Training examples. So here it implements the strategy by choosing what? Shorter trees over longer ones. Shorter trees over longer trees. Okay. Now it selects the tree that places the attribute with the what? Don't tell you've forgotten. With the highest information gain. So see, when choosing the shorter tree over the longer ones, how will it decide then? We've done this in the previous class. So based on what? Based on information gain. Okay. So the one that has the what? Highest information gain becomes our root node, right? So the preference must be here, higher information gain, not even higher, highest. We calculated that, right? So highest information gain, that we place at our root node. That becomes my root node. Done. Fine. So when we consider an algorithm that begins with an empty tree and searches the tree in breadth first notation, okay? Breadth first is called breadth first search notation. So what happens is it goes level wise, right? See, start, okay, check that first level, then again it goes to the next one. So horizontally it searches breadth first, it doesn't go deep like vertically, right? If you check, does ID tree mirror that? Yes. So what your ID tree does is it takes the tree, fine, after computing your root node based on your information gain, then it implements what? Breadth first search strategy, right? So it first considers the tree at what? Depth 1, right or wrong? Then it moves to tree at depth 2. You saw that. Okay, I will represent this again. So what we saw was, see, this is my root node, so this is over root node. Now with root node, we come here, no? We saw this, right? Then here it was already a pure leaf, so we didn't bother considering this. So this is my first level. At this first level, after splitting this, right, I did not proceed down, no? What I did was, I went to this side, right? Fine. So it goes level wise. Only then it moves to the next level, okay? So once it finds a decision tree that is consistent with all the training data, what will it do now? It returns the smallest tree that is consistent with the search space, right? That was what we saw here. Here it checked, right? And then finally we saw that there was no need to split it further, right? There was no need, okay? So it returns that tree. Can you see this is a, look here. Start, if you take this as the root node, so this is also a tree, right? A sub-tree of this, and this belongs to the main one. So this is the entire tree, and we have two sub-trees, right? Fine. So this is a sub, and that's also a sub. Fine. So that's what we are trying to explain here. Now, next, after this is done, ID tree goes with the notation that shorter trees are preferred over longer ones. So whenever you hear of the strategy, the strategy is telling you choose the shortest path first. Okay? So it's like traveling salesman problem. If you want to, okay, you are a vendor, okay, not you, okay, fine. You know these guys, Zomato, Uber Eats and all whatnot, right? Fast food vendors. So what they do is, if they want to get the parcel across a customer, obviously the cab drivers or the bike drivers, they have to find a way. You see, majority of the time they avoid traffic, right? Even they jump it also. Because their problem is, I need to get to this, to my customer in the shortest possible time, right? If you give me something, a food that is cold, obviously I will complain, no? So it's similar to what ID3 is doing. ID3 is like, see, I don't need to check all possible combinations before I arrive at my my pure leaf node. I'm going to follow the shortest possible path. And that is similar to your traveling salesman problem. Next, with that, we come to restriction biases and what? Preference biases. So we've seen this, okay? So you might ask, how is this strategy different from the candidate elimination strategy then? You saw that in candidate elimination strategy, there is no preference over which one was my root node or stuff. What we did in candidate elimination was just to generate what? Sets of hypotheses that will be consistent, right? With the training example, and that led us to what? Get into our version space. And with that, we were able to obtain what? We were able to reach a conclusion because our data sets were not, or our samples were not biased, right? So in this case, when we look into preference and restriction biases, so in preference bias, it's like which is asking you the question, which one should I prefer over the other? Have we not answered it? Which hypothesis should I prefer over the other? Or which set of assumptions should I prefer over another? Yet you know that we prefer. Now here we are talking of hypothesis now, or the biases here in this case. So, and here we spoke about tree. Shorter trees over longer trees led to the conclusion that shorter hypothesis will be preferred over what? Longer hypothesis, right? As simple as that. So when you look at this, the preference bias says that take shorter ones over longer ones. What are ones now I'm talking about? You think we are talking about ones and zeros, huh? Okay. So we are talking about what? Shorter hypothesis over hypothesis, longer hypothesis. So that's what this guy is talking about. So in preference, shorter. Preference bias. Shorter hypothesis over longer hypothesis. Similar to shorter trees over longer trees. So there are no hard restrictions on the hypothesis that can, we can actually generate, right? So this form of bias is called our search bias. So another name for preference bias is known as what? Search bias, aka search bias. Okay, how about restriction bias now? Is it that there will be sets of restrictions? Restriction bias. So this type of bias is known as language bias, because if you remember, in the case of a candidate elimination, okay, the algorithm was in the form of what? Categorical restrictions, right? On the sets of hypotheses considered. There was no such thing as drawing a decision tree in your candidate elimination, is that right? So when this was called search bias, remember we went what? Breadth first search, right? Here, so we call BFS in your preference. So this was what? Language bias. Language bias. Because we dealt with what? Categorical restrictions, right? So we dealt with categorical restrictions. Okay. So in the what? On the sets of hypotheses which we considered. So you know by now what categorical data are, right? Like, see, if I can actually say, give it a label, like say yes, no, true, false, right, wrong, like that, okay? So these are my categorical variables. Now, so this is it, okay? Now with this, we proceed to why do we prefer short hypothesis? Why do we prefer short hypothesis? Because we said here, no, that the preference bias places emphasis on shorter hypothesis, right? And then the restriction bias places emphasis on the language, right? Taking a closer look at what the categories which we saw from what? Our hypothesis. Next, when we say, why do we prefer shorter hypothesis? We need to back it up, right? So why prefer shorter hypothesis? Now, it was in the early, now this is the problem with, this is one of the cases with machine learning, okay? Most of the things we know in machine learning has existed, you know, we talked decades ago, but most of them has been there for centuries. Statistics, as you know, a kind of is a physical science, okay, in which you study what? Facts. You make out facts from figures. So usually statisticians are good at number crunching. They take data, interpolate it, give us meaningful insights into that. How old do you think that discipline is? How old do you think the discipline is? How about maths? How old do you think maths, the discipline mathematics, is? How about the brain behind those subjects? So one of such is Occam. Okay, actually his name is not Occam. We said Occam Razor. His name was William Occam. Okay, so I'll wipe here and then we take a look at this man. So why I prefer this? William Occam actually gave the law of parsimosity. Okay, now you get, okay, we might be thinking now. So William from Occam came up with the notion that simplicity equals perfection. So why prefer shorter hypothesis? Take a look at this. His name is William. From now, you see, we say Occam, O-C-C-A-M, right? But actually it's O-C-K-H-A-M. I think that's the correct spelling. O-C-K-H-A-M is a small city, they call it a parish, in Surrey. In small city, his name originally is William, okay? Small city in Surrey, and Surrey belongs to, is a, I think, yeah, a city in UK. Now, in the, I think in 1320, now, if you think now, 1320, which century is 1320? Okay, in the beginning of the 14th century. He came up with the notion that what? Simplicity equals what? Perfection. Proposed the notion that simplicity equals perfection. Okay? Now, and this Occam Razor, whatever, is a problem-solving principle, okay? That simplifies the solution using just what? The simplest approach, okay? So it says when presented with competing hypotheses to solve a problem, when presented with competing hypotheses to solve a problem, that one should select the solution with what? Fewest assumptions. So if you get back to our tree, just imagine that you have to split on one sub-node. Once you, maybe one sub-node has 2 splitting criteria, and another one has 5, another one has 7. So which one should you choose? You choose the one which has what? The simplest what? Assumption. By that is having fewer assumptions. Because even when you program in the industry, you know, companies tend to follow agile methodology. Okay, I don't know what they are following now. Okay, pardon me for that. So where we see we do things simple, you say keep it simple, simplest, or simple stupid. Make it simple in such a way that even if you leave the company, another developer who takes over the project will be able to understand whatever you've done, right? Why, okay, example, you want to write a program that will just add 2 numbers. You start by declaring so many variables, start by, maybe declaring 2, 3 functions. One function to accept the first if it is an integer, another to accept when it is a real number, another to accept when it's a floating point number. Then again, you now try, okay, to show us that you have very high IQ. So you write maybe like try to, instead of using basic operator, addition operator, you try to overload maybe another operator to do addition. So why all that? It's not necessary, right? So that was the principle of what? William Ockham. Okay? So he gave us this, the notion, and by the way, he was a philosopher, I think an English mathematician also, born in 1285, you see, and then he was born in UK, and then he died in 1347 in what? Germany, another province called Munich. Okay, M-U-N-I-C-E, in Germany. He died there. So why did I tell you little about him? Because when I heard of Occam Razor, okay, a simple Google search turns out that his name was William Ockham, and somehow the name, it just appeared strangely. It wasn't like a name that I was conversant with. So I tried looking up some stuff, and I found it interesting that he was really, really learned. Okay, so in short, Occam Razor. So now the next assignment will be, why is Razor attached to it? Because his name was William from Ockham. Okay, spelled at O-C-K-H-A-M. But where did Razor come from? You have to find out. So Occam Razor. Occam Razor says what? In short, prefer the simplest hypothesis that fits the data. Prefer the simplest hypothesis, the simplest hypo that fits the data, that fits the data. All right. So with this, we will wind up today's class. Okay. But before that, it's worth mentioning that, as with philosophers, right, you will also get opposing or digressing views, right? See, I think it was Galileo, I don't know. Okay, one of the Greek philosophers says that, I think it was Galileo, I don't know. Okay, he said that the world doesn't revolve, that the earth doesn't revolve around the moon. The sun, sorry. The earth doesn't revolve around the sun. I will repeat. In the earlier century, we had this notion whether the earth revolves around the sun or the sun revolves around the earth. So one of those philosophers came up with the idea that he proposed it, that actually the sun is stationary, the earth revolves around it. I heard he was stoned to death actually, because you're like, how can the earth be stationary? How can the sun be stationary and the earth revolves around it? If the earth revolves around the sun, why are we not rotating, right? I mean, we should move, no? So, with that came so many digressing opinions. That no, the earth is stationary, the sun revolves around the earth. Similar to such notions were the notion whether the earth was flat or it was what? Round. Some said that the earth was round, some said it was flat. Again, until it was proved in the late 17th century by observing sunrise and sunset, right? So observing seasonal changes and all whatnot. That since the earth rotates on its axis every 24 hours, that's why some places you have day and some night, proving that the earth was indeed spherical and not flat. So the same thing is applicable to Occam Razor's assumptions. Okay. So his notion were actually, he has also digressing notions. So we look at the one which was in favor of his hypothesis. So first one, the one that was in favor, we also propose alongside, and some of the philosophers also, his co-worker said, his co-mate says that's fine. Shorter hypotheses that fit the training data, okay, are less likely to be coincident. So see, I know, because if I take this, right, obviously it will not lead me to so many errors, right? So coincidence here is like, yeah, definitely I will not overfit my data. I don't want to use that word now, it's too early. Okay, so it will be coincident. I will be able to arrive at what? A tree easier, okay, instead of having so many levels of tree, right? So, and again, many complex hypotheses that fit the current training data might fail to generalize correctly to subsequent data, right? Yes, because see, where I have so many complex hypotheses, right? See, it's the reverse of that one, of the what? The shorter hypothesis. The shorter hypothesis invariably gives me what? A logical conclusion. I'll be able to get my tree easier. Similar to your what? Shortest path first procedure. But if I choose so many hypotheses, right? What happens? What? It will fail to it will fail to generalize, right? Fine. So what were the opposing arguments now? See, though there are few trees, right? That the prior chance of finding one which is consistent with the arbitrary sets of data is relatively small. It's the same, right? You have chosen smaller hypotheses. What have you done now? You have eliminated all other possible what? Combinations. Okay? So the difficulty here is that, you know, there are very many small sets of hypotheses, okay, that one can define. But in that case, those shorter hypotheses might not give us what? A more insight into designing the tree. So in such a case, usually shorter is not the best, right? The shortest possible path is always not the best path. And if you think of the size of the hypothesis, okay, since the size of it, right, is relatively small, okay, this hypothesis, or the Occam-Reza's hypothesis, will produce two different hypotheses from the same training example. Okay, see, if you think of it this way, look at this tree. Okay, so we come back here. It's okay, take care, fine. Here we just chose, and we have two possibilities here, right? So these two possibilities, again, if we split, okay, maybe we get another two more. Now, here, all those small subsets, right, will not give us a kind of an insight into the general table, okay, or into the general tree, sorry, not table, okay. So, with this, on this basis, we might be tempted to reject Occam-Reza's notion altogether, okay. So, his hypothesis, we might reject it. And you remember, it is consistent with our definition of hypothesis. Because we said hypothesis is like wise assumptions, right? Initially, when we started the class, I was like, okay, fine, I will believe that all girl students are smarter than the guys. That was my assumption. So if I finally prove it by looking at your performance, okay, in terms of your aggregate scores or stuff, then my first assumption is right. Otherwise, I have to reject that and say guys are more brilliant. The same thing here. We agreed, but we also echoed what Occam-Reza said, that shorter are always better. Now, in this case, now on the basis of us not having a clearer picture, okay, or drawing insights from the larger tree, we might be tempted to reject Occam-Reza's proposal altogether. Remember, we say we might because only in few cases that we reject. In other cases, we don't reject. So we have come to the end of today's class, but somehow I want you to remember how we started, okay? We started by first looking at what? The hypothesis search space in decision tree, okay? Now, taking a closer look at the search space of ID tree and what? Candidate elimination. We proceeded to looking into inductive bias in decision tree. And taking a closer look at the search strategy, okay, in ID tree. And that gave us the obvious question, why do we prefer shorter hypothesis, right? And then to answer that, we first of all need to understand what we mean by preference and restriction biases. The preference says what? always go with what? The first hypothesis. Fine? Which gives us what? Shorter hypothesis. Next, the restriction is not exactly as the preference, because in that we are not generating trees. What we did was what? We said, okay, fine. We looked at the categorical data, fine, and then we moved to the next thing, right? Which was what? The Occam razors hypothesis, which again backed up what we said, right? And we know that that was based on the notion that simplicity always equal what? Perfection, right? So, and it's a kind of a problem-solving principle that was developed by this famous philosopher. And shortly after that came what? Disagreements, right? Between him and his what? His peers. With some in support of it and some in what? In opposition. Those in support bought his idea, and those in opposition also proposed an alternate hypothesis. So if we take it this way, that Occam's razors hypothesis was the null hypothesis, and the other one was the opposed hypothesis was what? The alternate hypothesis. So with that, we will conclude today's class. I will see you in the next class, where we will look into issues in decision tree learning. Thank you.